Okay, chapter 2, derivatives. Hopefully this will be short and sweet. In pre-calc, we talked about the average rate of change, and that's the same thing as talking about the average velocity, and we use the slope formula, right? And so what we're going to do is look at that slope formula of the secant line a little bit closer. And I know you've seen this. This is just a review. So this blue point, we're going to go ahead and say that the coordinate point that matches with it is x comma f of x, all right? Instead of x sub 1, y sub 1, we're going to rename it this way. We're going to say we know there's a distance between x and this next x value for the pink point or the magenta point, and that's going to be x plus delta x. So the y value would be f of x plus delta x, and the coordinate point would be that. And so we're just taking the slope formula that we know, but instead of using y1 and y2 and x1 and x2, we're rewriting it in a different way, but it's still the same slope formula, right? And when we simplify the denominator, and we get that. Feel free to slow that down and just appreciate, that we could even look at the slope formula in a different way. We had to. We couldn't use, right? If we tried to use this and work some limit magic in there, what's going to happen? So we had to look at it in a different way. All right, so let's go ahead, and this is what we just did, and we're going to look at this idea of using limits. So we're going to have delta x become closer and closer to 0. We're going to scooch. See how x is being scooched a little closer to x plus delta x. So delta x has, the length of delta x has become smaller, and then even smaller, and even smaller, until it is the same, right? I know we say delta x is approaching 0, but it got so close to 0 that visually we couldn't tell. And so when we're looking at the slope formula as a limit, where delta x is approaching 0, it gives us the slope of the tangent line, which is, as we know, extremely cool. All right, so using this limit idea to get to derivatives, we're going to call that the definition of the derivative. So when you see this problem that asks you to use the definition of the derivative, that just means use the limits, use the long way. Everyone knows what the long way is. And yes, am I ever going to ask you to do this on the test? No. But it's really important to understand where our derivatives come from. So let's just do this one last time. So read the problem, go ahead and pause my video. But before you do, let's look at the remembers. Okay, we're going to add delta x to every x. So when we see x squared, we're going to put in parentheses x plus delta x quantity squared. Remember to distribute the minus sign to every term. So let's go back here real quickly. It's that minus sign right there in yellow that people forget to distribute to all terms in the function. And okay, that's good. All right, go ahead and pause, do this, and come back. Okay, so hopefully when I do the big reveal, it looks like what you wrote. If it doesn't, try to catch your mistake. And if you can't figure that out, we'll talk about that in class. And so obviously, what's the shortcut? Yes, we could just use the power rule. And once we find the derivative, if we want to know something very specific, the derivative at the points, we go ahead and plug in the x value of the points. All right, let's talk differentiation rules, constant rule, power rules. Let's go over that real quickly. So y equals 5, if we were going to take the derivative of that, I want you to just kind of think, y equals 5, 1, 2, 3, 4, 5 is just this line, right? And so what's the slope of a horizontal line? 0. But whenever we take the derivative of a constant, like the number 5, it's always going to be 0. All right, let's see what's behind number 2. All right, this is just something we're going to use the power rule. So the derivative, right, we can write y prime if we're talking about the derivative. We could write dy over dx. I think we're going to talk about that on the next slide. So we're just going to do the power rule. We'll have what? 30x squared plus 10x minus 4. All right, before I do the big reveal for example 3, this is a case where we will want to rewrite. We want to get this cube root into a rational exponent, right? And then we'll take the derivative, and then we'll simplify. So go ahead and pause, do it yourself, come on back, and hopefully this is what you have. We rewrote it, we took the derivative, and then we simplified it. It's just bad manners to have negative exponents in math, and so just make sure you remember how to how to change that. All right, same thing here. We're going to do a rewrite. We're going to take the derivative, and we're going to simplify. Pause the video. All right, should be what you have as well. So what I like about me saying pause the video is you're doing the work to see what you remember. And you know what? It's okay if you make mistakes as long as you understand, oh, I did it because of this. Just like in class, usually our mistakes are going to be algebra. It's not about the calculus. It's about the algebra when we make mistakes. Well, at least at this point it is. All right, find the equation of the tangent line at x equals 3 for the function y. Okay, so what is this asking us to do? It's giving us a function. It's asking us to take the derivative, right? Which gives us the rule that we use to find the slope at certain x's, right? Or the derivative at certain x's. So it's asking us to find the derivative, plug 3 in. That's going to be our slope. And then find when x equals 3, what's the value for y. So that's our point. We have our slope, we have our point. And you can either use point slope formula or slope intercept. Your choice. Pause it, and let's see what we've got. All right, hopefully you've done it, and let's see what. So here's the derivative, and we plug 3 in, and we got 16 is the slope of the tangent line at x equals 3 on this curve, right? And so now we need our point. And so when we plug 3 into our function, we get 14 for our y value, right? So here's our point. Here's our slope. Here I used point slope, right? Or you could use slope intercept. You get the same thing. I don't care which form you use. Point slope is easier if you have that memorized. Slope intercept, what you save yourself, 2 seconds using point slope. It doesn't matter to me which one you use. All right, let's look at graphs for a little bit as we're talking about derivatives. Where does the derivative equal 0 over the interval from -9 to 9? All right, yes, we're talking about horizontal tangents. And so when I'm looking, let's see, I look and see one. It's a little hard to see on the smartboard. I can see it better. I'm going to go ahead and just look on my computer. I know you have no idea what I'm doing, but I can't even see the grids on the smartboard. All right, so it looks like we have a horizontal line, whoop, at -4, and it looks like we have one at 1 and at 6, right? So -4, 1, and 6. And I know what some of you might be thinking. You're like, how about -6? And so, right, sharp turns, we got to be really careful with sharp turns. And I'll show you why. Like, as we're coming along, let's draw the tangent line. Looks like tangent line there, tangent line there. Okay, and then over here, there's a tangent line. Whoops, not like that. All right, this is when I need to go back to the board. Let's see what I have. I had a tangent line there, kind of like there. And then on this side, I have one there. All right, who knows what's happening between all these red lines? Tangent lines. Could the tangent line at the turn, the sharp turn, be there, or there, or there, or there, or there? Right, we don't know. That's why there's not a derivative there. There's the derivative's undefined at sharp turns. And I think that's what we have behind this orange blob. Oops. Let me see if I can get back to, there we go. All right, it's continuous at x equals -6, but it's not differentiable because of the sharp turn, right? And how can we tell? It could be any of those purple lines. It's a million different ones it could be. All right, where is the derivative undefined? So we're looking for vertical tangents. And so let's see, it looks like we've got one here at -5, right? Oops. And we've got one at 6. Right? Are those the only two? Hopefully you can see the grids. I'm having a, okay. Once again, we have a sharp turn. So at, let's see, so at 6 we have, it's undefined. At -5 it's undefined. And at our sharp turn at 1 it's undefined. All right, let's see what's behind this box. Okay, so even though the graph is continuous at these points, it is not differentiable there. So note these last 2 slides, I've been hinting at, comparing and contrasting these ideas of continuity and differentiability, right? And I think we're going to pull that all together in the next one. We will see. Oh, we got one more. All right, discuss the value of the slope of the tangent line at various things. All right, let's see what it wants us to do. At the derivative at 1, all right, well, right, we've got that horizontal, so that's 0. And then the derivative at 6, it looks like we've got that vertical line, and so that's undefined, right? Intervals over which the function has a positive derivative. All right, let me get rid of these purple. So we're just looking for where is the graph increasing. So it's increasing from -7 all the way till, gosh, it's hard to see on this. How many times am I going to complain about that? All right, till -4. So it's increasing from -7 to -4 and increasing again from 4 to 9 and from 4 to 9. All right. And then over which it's decreasing from -4 all the way to +4. All right. Let me check on the time. All right, so this is going to pull it all together. Let's see what's behind here. All right, we talked about the average velocity, which is the slope of the secant line. We didn't really talk about this because we were just talking about the slope of the tangent line, but obviously that's instantaneous velocity. That's how fast is the change at the point, instantaneously, not over a period of time. It's at that exact time, so that's pretty darn cool. All right, different ways to write the derivative, right? We can write f prime of x, or we can write y prime, or write dy over dx, or d, and then write the actual function over dx. So dy over dx, I understand that to be the derivative of y with respect to x. That's what it means. All right, once again, we know no derivative at a sharp turn. We get it. And then, oh, this is interesting. The blue line, it's still a tangent line, even though it crosses through the curve again. It's still considered a tangent line to that pink dot. And then differentiability implies continuity, but not the other way around. All right, we've seen 2 examples of something that's continuous, but yet not differentiable with those sharp turns. So remember that. Okay, Delta Math 2, number 2 covers this. We're going to do that in class. All right, let's look at the product rule. And so basically when we've got 2 functions that are being multiplied together and we're finding the derivative of it, we take that first function, we take the derivative of it, and we multiply it by the second function. And then we add that to just rewriting the first function and taking the derivative of the second. All right, so when we see this, we're like, our first function is 2 minus x cubed, and our second function is sine x. So whenever we see trig, we're like, whoa, okay, let's remember the trig derivatives. And so I'm going to ask you to, if you haven't memorized these, or you memorized them and you forgot, recommit them to memory, because this course it's got a lot of memorization in. It just makes sense. You've got to memorizing is like the first thing we do so that we can use what we've memorized in big and amazing and expansive ways. So let's memorize. Let's do it. So I know that if you think about the Pythagorean trig identities, the secant, so secant squared x equals tan squared x plus 1, right? And cosecant is cotan squared plus 1. I always make a little joke about, like, I went to college in the 80s. That's not a joke, that's real. And I was in a sorority. I was a tri-delta. And anytime that, it was a long winter, we all couldn't wait for the first decent spring day because we would go and seek a tan on our sorority house patio. So that's how I remember seek and tan go together, seek a tan. And so you notice with the derivatives that they're still attached with each other, right? So that's And I know it's silly, right? It's silly that I told that story, but once again, to memorize, you have to come up with novel ways to think about something because your brain loves novelty, right? And it'll remember. Same thing, seek, seek a tan. And then for this, I think about when we were in kindergarten and maybe you had a stuffed animal that you would grab your stuffed animal in kindergarten during nap time and you would co-seek a cot. Okay, you take that stuffed animal and you and your stuffed animal would co-seek a cot to take a nap on. You get it? Okay, so, and then once again, see how co-seek and cot, co-seeking and cot go together. So that's one thing you may decide to use. Whatever you decide to use, once again, the identities, do we ever use these identities in calc? You know, we might, I don't know. I don't know because I use them all the time because I teach pre-calc all the time. But don't worry about the identities now. We will have a chapter where we focus more on trig. So right now, memorize these derivatives. And let's go back and do the problem. All right, so we're going to rewrite. We're going to take the derivative. We're going to take the first and take the derivative of it. The derivative of any constant is 0, so it's going to be 0. The derivative of minus x cubed is going to be minus 3x squared. And then we go ahead and rewrite the second function, which is sine x. Then we're going to do a plus. We're going to rewrite the first function as it is. And we're going to take the derivative of sine, which is cosine. So you know, this isn't, we're going to go ahead and distribute. There's nothing fun that's going to happen here, like all of a sudden, like, oh, we get to combine things, and oh, was a fun surprise. There's no fun surprise here. So we're going to have plus 2 cosine x minus x cubed cosine x. All right. I wanted you to notice another thing that I do to remember is that, see this, that the derivative of cosine is negative sine x. And I always think, oh, that makes sense that our answer would have a negative when it's about sin, right? Sin, that's a negative to sin. Okay, haha. Once again, I'm going to be offering these goofy ways to remember. It does help me, but you can come up with your own ways. And then it's interesting because, ooh, what's the reciprocal of sin? Cosecant. That's right. Cosecant's got the negative, right? All right, so the only ones that have negative, as far as the derivative answer, the actual derivative, is the sine x, and then the 2 that have the cosecant in them. All right, let's go ahead and it makes sense once we do, I'm sure you probably did this last year, once we learned the quotient rule, right? You could take the derivative of cosecant if you write it as 1 over sine, and you could take the derivative of tan if you do it as sine over cosine. Probably had fun doing that last year. All right. Oh, I think I had fun. I think this is on here because I think last year they wanted to know, wait, why is cosine the derivative of cosine's the derivative of sine? And I think what I did is I started out with the sine graph in green, and then I kind of went through and showed them, well, what's the derivative at 0? The derivative, you know, the tangent line, the slope of the tangent line is 1, so that's where this 1 came from over here, right? And then what's the derivative at pi? That would be the negative 1, right? And then, of course, we've got the 0 right here. We've got the tangent line of 0, so that's why it's 0 there. So pretty cool, right? If we really took the time to, oops, there's a 0 there. So this is where our 4 points came from, looking at sine and finding the derivative of the obvious ones, the 1 and the 0. And so we get the cosine graph, right, which is pretty cool. All right, I know I'm going fast. I'm hoping that that's a good thing because those of you that remember can just get this over with. And then those of you that kind of have forgotten a little bit, you get to slow it down. All right, so here's the deal. If I looked at this, I could find the derivative by using the product rule, right? But before I use any rule, I'm going to always think, rewrite, and take the derivative the easy way using the power rule before I do any. So I want you to pause this, and I want you to do it both ways. Rewrite and find the derivative, and then find the derivative using the for the product rule. So go ahead and do that pause, and then come back, and let's compare our work. All right, so hopefully you have this done. In this case, the rewriting was so much easier. And it's funny because this is going to be true. We're always going to be on the lookout for rewriting and using really more when we start integrating too. We can rewrite the integral and integrate a lot easier. But whenever you can make it easier, make it easier. But also I wanted you to have fun, haha, fun, with this product rule. Looks like fun. All right, once again, if you have questions on this, you know I'm there for you when you come into class. All right, so the last rule we're going to look at today is the quotient rule. I kind of think when I look at the quotient rule, I think the denominator is the boss. I mean, that's just what it looks like because, you know, it gets all the action. Not only does it get squared in the denominator, it starts first in the numerator. I just kind of think about it that way. So we're going to make sure that we know the denominator starts the show, but just by rewriting it, not taking the derivative. And so I'm going to give you another one where you can use the quotient rule or you can rewrite, take the derivative and simplify. I want you to do it both ways. Just to get, once again, the algebra is really what we're doing. The calculus is just the rule. I mean, the rule is just memorizing. So it's the algebra that I want you to practice right now. All right, pause it, do it both ways. All right, we're back. Check your work. Obviously, still breaking it up, rewriting it is just so much easier. What a mess. I don't know, can you even see this? Let's see if I can make it bigger. Oh, nope, I can't. Let's see. All right, let me get rid of this. Now let's see if I can make this a little bigger. All right, so hopefully you can see that. There. It looks like chicken scratch a little bit, doesn't it? All right. Let's see, what else do we have? That's it. All right, so in class tomorrow, we're going to do Delta Math 2 and Delta Math 3. We're going to just stop by the quotient, as soon as we're done with the quotient rule stuff. And then all we have left is implicit differentiation. Oh, changed my mind, sorry. Chain rule, implicit differentiation, and related rates, which that's really a lot of fun. I think all three of those things are fun. All right, thanks for joining me. I will see you in class.